In this video, we'll be looking at an example of the trapezoid rule over a quadratic using specifically 4 rectangles. So the first thing I'm going to do is I'm going to go ahead and graph this image to give myself an idea of what it is I'm looking at. Now if I graph this quadratic as accurately as possible, again we're going to have this thing cut from 0 to approximately 4 into 4 rectangles. So conveniently enough, if I can identify what my delta x is, just like I would in any Riemann sum problem, b minus a divided by n is going to be b, which is 4, minus 0 divided by 4. And the distance between each rectangle, or in this case trapezoid, is going to be a distance of 1. So there's the first section, there's the second section, there's the third section, and finally there's the fourth section. So my goal here at this point, let's see if I can make that as straight as possible. My goal at this point then is to take all 4 of these sections and turn them into clear trapezoids. Now I'm going to do that with a red pen, so hopefully it'll be better for you to see. There's one trapezoid from there. There's a second trapezoid. There's a third trapezoid. And then there's the fourth one. Now you'll notice each of these trapezoids, in some aspect or another, they're just a little bit of an over-approximation. But this is definitely a more accurate approximation than any rectangle we could have used in most cases. So let's go ahead and evaluate each piece that we need to have. First off, again, my trapezoid rule is the summation of 1/2 f of xi plus f of xi plus 1 times delta x. So I've got my delta x. I have each individual endpoint that I might have to use. Now let me go ahead and just start with area 1, and then I'm going to go through area 2, area 3, and area 4. I'm going to go ahead and evaluate all 4 of those different rectangles. So for area 1, I'm going to go ahead and have, one more time, 1/2, in this case height 1 plus height 2, times the base. Well, what's the base? The base is that value 1. Again, base is almost always going to be equal to that delta x. So I'm going to have 1/2 times a couple of values times the value of 1. Now what's my height values? Well, remember, height 1 is going to be this distance from, in this case, 0 to 0. So h1 I'm going to label as f of 0, plus h2 is going to be the distance that I have to go, so I'm going to be at this endpoint here, but that distance is whatever f of 1 happens to be. So I'm going to go ahead and plug in 1. This gives me 1/2. Now remember, your function that you're playing with, f of x, is this x squared in the original integral problem. So I'm going to have 0 squared plus 1 squared all times 1. So this is the area of the first trapezoid, which is nothing more than, again, 1/2 times 1 times 1, so 1/2. If I continue doing this process, a sub 2 is the area of the second trapezoid, which is this distance right here. So I'm going to need the endpoint of the value of 1 and the endpoint of the value of 2 for my heights. And then my distance between the two, again, for the base is 1. So without having to rewrite this formula 100 times, I'm simply going to write 1/2 times, I want f of 1, the starting endpoint, plus f of 2, the ending endpoint in that interval, all multiplied by my delta x, which is 1. In that case, I'm going to have 1/2 times 1 squared plus 2 squared times 1, which is, once again, 2 squared is 4, plus 1 is 5, times 1/2 is 5/2. So now I have the integral, I'm going to write this down here, the integral from 0 to 4 of x squared dx is approximately equal to, area 1 is 1/2, area 2 is 5/2. I'm going to have to figure out what area 3 and area 4 are. Well, the area 3 is the distance between 2 and 3, and again, the heights of those two values averaged. So that's going to be, very quickly, a sub 3 is 1/2. I'm going to have 2 squared because that's my starting point, and I'm going to have plus 3 squared because that's my ending point, all times 1. And my area 4 is going to be equal to 1/2 times my starting endpoint is 3, and my ending endpoint is 4. And again, I'm not arbitrarily squaring these numbers. I'm squaring these numbers because that was the function that we were using in the interval. Those values, this one here and this one here, are the heights of the endpoints, or at those endpoints, up to that function. So when I evaluate these two, I'm going to have 4 here, 9 here, giving me 13, so 13/2. Let me check that one more time. 4, 9 is 13. And then 9 plus 16 is going to be 25, and that's going to be 25/2. So I now have all of my approximated trapezoid values, and I can simply add those up, giving me, looks like, 30, 44 halves, which is nothing more than 22. And again, in this case, if I had a unit of measurement, I'd call it units. But it appears that the area under the curve from 0 to 4 is approximately 22 units.